So, now we will see the internal energy of an ideal gas. So, in this session we will see internal energy of an ideal gas, and two important points we will learn which are derived from kinetic theory, that is the idea of degrees of freedom. Degrees of freedom, and one important point, equipartition theorem. So, these two things we will also learn, and sorry, this is not derived from kinetic theory, this is done by Maxwell's by statistical thermodynamics, and we will use these two concepts along with kinetic theory of interpretation of temperature to derive the internal energy of an ideal gas. So, internal energy of an ideal gas we will talk. So, let us consider a monoatomic gas. So, according to the kinetic theory, i.e. the kinetic interpretation of temperature. So, we have already seen that is 3/2 kT is equal to half m c square, that where c is RMS velocity. That is, we can say that this is 3/2 kT is equal to K average, i.e. the average translational kinetic energy of a monoatomic gas molecule. So, this is the average kinetic energy of a monoatomic gas molecule as predicted by kinetic theory, which we have already covered in our first session of kinetic theory. So, now the important point is that how I can associate the internal energy of a gas. So, you see thus the only energy possessed by a monoatomic gas, gas containing monoatomic gas molecules. Thus, the only energy possessed by a monoatomic gas is the kinetic energy of its molecules. Since the molecules does not interact, so they do not possess any potential energy. Thus, the entire contribution to the internal energy of a monoatomic gas comes entirely from the kinetic energy of molecules. So, now if a gas contains total of n moles, i.e. n is equal to n number of moles into Na number of molecules, then its internal energy will be is given by U, that is internal is equal to this N into 3 by 2 kT. This is the average energy of one molecule. So, total N molecules. We will write N as N into Avogadro number Na into 3 by 2 kT. So, we have U is equal to, we can write 3 by 2 kT. Now, we see here K is Boltzmann constant and this is R by Na. So, we write this K as R by Na. So, let us replace this K by R by Na. This is T. So, this Na cancels, the internal energy becomes 3 by 2 nRT. So, number 1 point, thus we see that the internal energy is the function of temperature. So, very important point here, let us mention, thus the kinetic theory predicts that the internal energy of an ideal gas is a function of temperature only, dependent on temperature. So, you come back to this point. Here the total energy U is the energy of a single molecule into the total number of molecules. So, we should now stress that this is a monoatomic gas molecule, it contains 3 by 2 kT energy. If it is diatomic, polyatomic molecule, then what are the different ways in which it can store energy. So, now very important point, let us see that the internal energy of a gas will depend on the possible ways in which a molecule can possess energy. Very important point, let us write this here. So, the internal energy of an ideal gas depends on the number of ways in which the molecule can possess energy. So, we will see, and so this will be decided by what we call degrees of freedom of a gas, that is the number of ways in which we are going to store energy in the molecule. So, this factor into N will give the internal energy of a gas.